Welcome back from lunch. I hope that we don't compete too much with your stomachs digesting. Yesterday, Doug Irwin talked a bit about evolution and extinctions and over billions and billions of years. I want to tell a little anecdote about an extinction that didn't happen, which has a lot to do with a bifurcation that means that our next speaker is actually with us. Otherwise, he would not have been with us. I'm Kerry C., and I'm the director of the Earth Observatory of Singapore, and I guess Wang Xian Feng's boss at the moment, although you don't boss around scientists, right? They're like herding cats. Back about 25 years ago or so, let's see, longer than that. Yeah, about 25 years ago, Jerry Wasserberg, who was a well-known, renowned geochemist at Caltech, and still kicking around. He and I were two of the faculty members in the Geological Sciences Division that were on a retreat down to the Frank Capra Ranch. You know, Capra was the famous movie producer, especially for his movies back in during the World War II and so on. And we were down at the Capra Ranch, which had been given to Caltech for retreats such as this, and big grove of avocados and orange trees and whatnot. And so Jerry and I were there talking with the rest of the faculty about what direction the Geological Sciences Division should go. And one evening he said, "Could I talk to you for a minute? I've got a big problem." And so we went walking through the avocado grove, and he says, "You know, I've got a grad student that I want to kick out. He's just not performing. He's playing volleyball and having a good time, and it's just not right." And he was already in his third year or so, and he'd been one of my students. I thought he was doing pretty well, actually, and so I was surprised to hear that Wasserberg was so distraught about this guy and that he was going to just kick him out because he wasn't worth the salary. It wasn't worth paying the tens of thousands of dollars to keep him. And I said, "Well, you know, my experience was he's pretty good, actually. I don't think you should extinguish him. I don't think you should boot him out. I think there's still a lot of possibilities." And I don't think that I influenced Jerry much about this at all, but he did finally decide not to extinguish this graduate student. And it turns out that this graduate student, Larry Edwards, went on to become the premier utilizer of the uranium-thorium disequilibrium method for dating things. So dating corals, and for the most part, but also now speleothems and so on. And so Larry's lab now at the University of Minnesota is the foremost place in the world for precisely dating climatic events, precisely dating falls in sea level during the last glaciation and the later rise to current levels. So Larry became the prime practitioner of this important field for climate studies, and it turns out that that Wang Xian Feng is Jerry's academic grandson. Okay, so Xian Feng is actually one of Larry's most recent students, and so today I have the pleasure of introducing Wang Xian Feng. You can read about him in the guidebook. I want to say a bit about what he's going to be talking about, though. I had never heard the two phrases that Johan used before lunch. The Eden, what was it? The Eden of the Holocene, or the humanity's 10,000 years of grace. What Xian Feng is going to talk to you about is minor perturbations that one can see in oxygen isotope measurements, very well dated by uranium-thorium, in Chinese caves. And what those minor perturbations did, what they tell us about physical things, the natural things that happen that influence the politics of Asia. Okay? So what you're going to hear now is a bit of science, uranium-thorium dating of oxygen isotope records from caves, and what it tells us about rainfall in China over the last few millenniums. Xian Feng?
Thank you
An example
so much.
of a good bifurcation in evolutionary history.
Thank you, Kerry. So it looks like you already gave the talk already. No. Is that clear? Also, thank you for inviting me. I'm very happy to have this opportunity to talk to you, to show you a story, a blender of the geology chemistry and climate and social science. So maybe you're also wondering, of course, it's a complex story, but maybe wondering how this guy can do it. So anyway, it's just a simple view from the caves. But I would argue, so this exactly fit the workshop theme. We are looking at a crude view of the whole. So in my talk, I want to talk about 4 things. So first, at the beginning, I want to set up why we want to look at these particular geological rocks, the rocks we can find from the caves, and what kind of data we're looking for, and what kind of interpretation, so what kind of story we can say on these rocks. And second, I was going to present the 2 kind of very beautiful records we produced by studying these rocks we collected from the caves, from China, from many other places, US, Brazil, and India also. And of course, we also wanted to link what we found from the rock samples. This is, of course, the chemistry composition variation, how this can be tied to the Chinese culture change, because we know that China has a very long history, and the culture of the China has been very well documented in historical documents. So we are intrigued to compare our data, which we try to interpret it as a climate change, to correlate it, to compare with the Chinese history. And the third, I also want to say, what we found in China is not particular for China. We can also find the similar correlations from everywhere else in the world. And lastly, this is the so what part. So what kind we can get? Can we just simply say the past is the key for the future? So how many of you have visited the caves, by the way? Quite a lot. That's great. So if you haven't, I would very strongly suggest you to see some caves. It's a very different world, underground world. So if you visit a cave, most likely you will see a variety of chemical formations. Some are hanging from the wall, some are growing from above, from the floor. For example, like this one, the stalactite, stalagmite. This is a particular chemical formation we want to work with. So simply speaking, the formation of the stalagmite is because of the rainwater. So when rainwater reaches the ground, suckling the soil is full of the carbon dioxide because of the organic decay, because of the root respiration. So when this water dissolves the carbon dioxide, this water becomes acidic. And then when this water passes through the cracks of the limestone, this water can dissolve the calcium carbonates from the limestone. So this is simply a carbonated dissolution process. The calcium carbonate plus water and plus CO2, and then form the calcium ion and the bicarbonate ion with a little bit of a carbonate ion. And when this water enters the cave, because the carbon dioxide concentration or partial pressure in the water is higher than carbon dioxide partial pressure in the cave air, so the CO2 can degas, can move out from the water to the cave air. Then that will cause the calcium carbonate concentration in the water becomes supersaturated and then precipitate out of the calcite. So this is simply carbonate precipitation process. So back to the dog. Evan said yesterday, because as a geochemist, we can do very well on the timing. So this is, we are looking at the radioactive isotopes by looking at the uranium-238, one of the isotopes, the major isotope of the uranium. This is the method my PhD advisor, Larry Edwards, as Kerry said, he developed when he was a PhD student at Caltech. So uranium-238 has a half-life around 4.5 billion years. That means after 4.5 billion years, half amount of the atom of the uranium-238 will be decayed away to form the daughter isotope. Only half amount of the atom can be left. After another 4.5 billion years, I think only 1/4 of the uranium-238 atom can be left in the system. But here, we are looking at the 2 intermediate daughter isotopes, of this decay, the long decay chain. So these two guys, the Yuan 234 and the thorium 230, so their half-lives are moderately long, around on the order of the 100,000 years. So we can use this system to date geological samples, mostly calcite, or sometimes aragonite. We can date the samples as young as 1 year, up to 800,000 years. As you can see, we can also date the samples very, very precisely. Of course, this is one way is because of the chemical, how well we handle the samples in the chemistry lab, but the other is because of the advancement of the machine, mass spectrometer, by the way. What I show here, so this is the slab, the rock slab. We cut and polish the surface of the sample. One of the calcite stalagmite. So when the calcite precipitated from the water, the uranium tends to goes in the rock because under the surface condition, the uranium has a very high solubility in the water because of the +6 charge. But the thorium is not. Thorium has very negligible solubility in the water. So that's the way we can separate these two elements in the rock. So simply speaking, by looking at this sample, we can count the atoms of the uranium and count the atoms of thorium. So we can assume the thorium 230 all comes from, or decayed from, the uranium 234. And then simply, we can apply to we can do the measurement on the mass spectrometer. We can apply to the equation, so we can get the age of the sample. So by being a geochemist, we not only can get a very good timing of the rock sample, we can do a lot of things, additional things. So here we're looking at the stable isotopes, which is oxygen, the element that we cannot survive without it. By looking at the equations here, the calcite dissolution process and the precipitation process, we can find that the calcite and the water, they share the same element, which is oxygen. So by looking at the samples, oxygen in the calcite carbonate, we can trace the oxygen to the dripping water. We can also trace the dripping water to the surface water, or even up to the cloud, the water vapor in the cloud. And oxygen also has isotopes. There are 3 isotopes, by the way, 3 stable isotopes. But the most two common ones are oxygen O18 and oxygen O16. So they share the same number of the protons in their nucleus, but the different number of the neutrons. So oxygen 18 has 8 protons, but 10 neutrons. And oxygen 16, 8 neutrons and 8 protons. These 2 isotopes, they can fractionate, although they share more or less the similar chemical behaviors, but during the physical process, they do fractionate, although with tiny, tiny change. But by using mass spectrometer, we can measure such a change. So this change is related, of course, to the temperature, but also related to precipitation amount, and sometimes to the source of the water, where the water comes from. We are living in Asia, and of course, we are familiar with the wind and the rainfall, for example, in Singapore. But if we look at the larger, this is summertime, the surface wind field. We can see it's dominated by a big wind blow from the ocean side to the continent. So this is simply because of the temperature gradient between the continent and the ocean. Most of us probably heard about Indian summer monsoon and East Asian summer monsoon. But meteorologically speaking, they essentially belong to one system. So when the wind blows from the Indian Ocean to the Indian subcontinent and move further to the Indo-China Peninsula and to the China coast and further inland, the wind also brings potential rainfall. So over the last decade, I have been working very closely with my colleagues in the US and China and a couple of colleagues from India. So we studied the caves and the cave samples from from China and a few spots in India. So we try to look at the cave samples and bring back to the lab and do some chemical studies on the samples. What we try to look at is the climate information to be preserved in the rocks. So here, what I present here, so this is our colleagues put together simply based on today's observation, the instrumental observation from a dozen of meteorological stations. What we can find is from the summertime, the June, July, August, when the monsoon comes, the 018, which is 018-016 ratio of the rainfall, also changed. The change to a depleted value. What we can get from this diagram is when the monsoon is getting stronger, the rainfall is getting higher because the wind carries the rainfall. At the same time, the 018-016 ratio of the rainfall decrease. So this is a very important observation. Of course, quantitatively, we still feel challenging to directly link these two, the rainfall and the monsoon strengths. But broadly speaking, we can say the lower the 018 value, the lower 018-016 ratio, which suggests the stronger rainfall, a stronger monsoon, and the higher rainfall. So please remember, so this is basically the observation we can get from today, and we will apply to what we can get from the geological rocks. So we have been very successful to put together the monsoon record by studying the cave samples. So what I show here, so this is the record through the last 300,000 years we put together by combining the different samples, the geochemical records from the different samples. As you probably see, the loss of the up and down, the loss of the wiggle, the up and down of the wiggles. This is to show that the 018 record. As I plot here, the weight means the value is more depleted. The interesting thing is we can also compare the record we found from the geological rocks with the insolation. So this insolation describes how our Earth, our planet, orbiting the sun. Because this is not a circle, it's an eclipse. And our Earth itself is also tilted from the vertical axis. And also the Earth is wobbling. So insolation is a parameter to describe insolation. So it's a combination of the parameter to describe how the Earth is rotating the sun and rotating by itself. It turns out the different parameters can change how the Earth receives the solar radiation. So clearly we can see these two curves, they match each other very, very beautifully. But of course, the main record I want to show you is for the last 2,000 years. Or in a way, it's a kind of comfortable time zone Johan just mentioned from previous talk. So this is a record we developed from a cave rocks we collected from a cave, the Wang Xian cave. This cave, by the way, is located very close to today's monsoon fringe area. So in the place very close to, in the middle of the Xi'an and Lanzhou, Gansu, as you can see, this light blue shows the fringe of the monsoon. So here's the record. So by the way, if we look at the x-axis, this shows the timing. So simply speaking, so we're looking at the time series we call it a record. So the time is 800 years AD, and here's the today or present, the 2000 years AD. And we also put the name of the Chinese dynasties here, the Han and back to the Qing dynasty. As you can also see, also show this kind of tiny, the pink bar here. These are the days, the uranium thorium dates we can get on the samples. So as you can see, we can get a very precise dates. The error bar, the analytical error bar is very small. So the error is already within 1 or 2 years. But of course, if you consider some other uncertainties, the error bar is on the order of 5 years also. And on y-axis, this is 018-016 ratio. The same thing I want to point out is that when the value is lower, that suggests the monsoon is stronger and the rainfall is higher. Of course, when we wanted to interpret our record as a rainfall signal, you're always wondering how robust it is, how confident we feel it. At the beginning, we did question ourselves. So the way we try to do is, we compare with the historical documents. Our Chinese colleagues, they combine together by looking at the regional chronicles documents from their counties. So we benefited from their work. So this is what they combined together. So they called it the drought and flood index. By simply count how many years, say over a certain time period, say 10 years, they could have a drought or flooding. So they quantified from 1.1 means the very drought, the severe drought, and 0.5 the mild drought, 0 is the okay climate, okay years, and to 0.1, which is a severe flooding. So you can see these two records, or these two curves, they match each other pretty well. The thing about it, there are two completely different things. One is geochemical variations we developed from a rock. The other is literature document. So this is really amazing, these two curves, they can match so well. So we feel very confident that our record can record the rainfall change from this region. But whether we can say anything about the monsoon by simply looking at one cave sample. So we want to compare with another cave record. Our colleagues, they developed from a cave in Central East India, the Dandak cave. So this actually is reported by a group from the University of Southern California. That record is not longer enough, but that record does have a portion of the period overlap with the record from the Wang Xian cave, as you can see here. Once again, this shows a very beautiful correlation, very beautiful consistency between the two records. So one is India, and the other is a further, one is India is located upstream of the monsoon, and the other is located further downstream, so close to the fringe of the monsoon. So we feel very confident our record can indeed represent the monsoon change. So as I mentioned earlier, so the China is very rich in the culture, very rich, and also it's very well documented historical. So we want to, since we want to interpret our record as a climate, as monsoon change, we want to compare our record with the historical documents. So here, I want to walk you through the Chinese history by looking at the 5 particular time periods. The 2 time periods, they corresponding to lower delta 018 value, which is wet climate. The rainfall was abundant. And the 3 time periods, or 3 time snapshots, when the climate wasn't good enough. So it was a dry periods. So the first snapshots we're looking at, so this is corresponding to almost the lowest value of the 018, 016, which we want to suggest this is probably the rainfall was the highest over the last 2,000 years. So this, by the way, is corresponding to the Northern and Southern Dynasties in one time of the Chinese history. So the Northern Qi is one of the kingdoms dominated during that time. During that time, the China was separated into different kingdoms, but Northern Qi was a very strong kingdom controlled in the northern part of the China. So one of the popular song was written during that time, the Chinese Schiffer song. So I still remember when I was a little child, I learned this song. In fact, this song is still being taught in Chinese elementary school. The boundless grassland lies beneath the boundless sky. When the winds blow and grass bends low, my sheep and cattle will emerge before your eyes. It's a very humanic, very beautiful scenery, the nomadic life. However, this site described by this song is located in Indo-Mongolia. It's very close to today's desert, very close to today's Sergipe. So if we go to this place today, by no way you want to sing this song anymore. So clearly suggests that 1,500 years ago, the climate was much wetter than today. So the second time window I want to show you is the Tang Dynasty, the last few decades of the Tang Dynasty. Tang Dynasty reached the highest point of the Chinese history. So it's one of the golden age, the golden time of the Chinese culture. During that time, the Tang Dynasty was one of the dominant countries in the whole world. Of course, it had big influence of the surrounding countries through military conquerings, through the commercial trading, and of course, the cultural exchange. However, if we look at the last few decades of the Tang Dynasty, we found our 018-016 ratio in the record was low, which suggests the possibility the drought times during that time. So in fact, if we look at the Chinese historical documents, we found they've been very well written that during that time there are multiple droughts occurred. For example, in AD 875, there was a severe drought in China, in the central part of the Tang Kingdom. And locusts swarmed over the land. And in fact, there a loss of the peasant uprising. So Huang Chao, he was one of the leaders of the peasant uprising. Of course, the Huang Chao uprising didn't bring down the Tang Dynasty immediately, but the peasant uprising clearly destabilized the Tang Dynasty, and which eventually led to the end of the Tang Dynasty. So 50 years after the Tang Dynasty collapsed, China entered another golden age. This is Song Dynasty, which lasted from about 960 to 1279. But sometimes we separate the Song Dynasty to Northern Song and Southern Song. Song Dynasty wasn't successful in military campaign, but Song Dynasty also had a very, very strong economy. So now if we look at the records we have, the records we got from the Chinese cave, we found this actually is corresponding to another very low value of 018, 016. So the very wide time periods. So indeed, if we look at the Chinese history, during the early few decades of the Song Dynasty, the Chinese population dramatically increased, even more than doubled, within about 50 or 60 years. And the rice became the staple of the Chinese diet. The rice cultivation dramatically increased. Even the rice was even be able to cultivate it in northern China, close to today where Beijing is. This is by no way we could understand it today. By no way we could imagine. So you could plant rice close to Beijing. However, the Song Dynasty was conquered by the Mongol Empire. So Kublai Khan, he defeated the Song Dynasty in 1279. He established the Yuan Dynasty of the Mongol Empire. However, the Yuan dynasty wasn't successful to maintain the dynasty. Although, of course, Yuan was very successful in strengthening his military power. The Mongol Empire could even extend to East Europe or even close to the Mediterranean Sea. If we look at the record, most of the time the Yuan, the climate wasn't very favorable, particularly during the end of the Yuan, a few decades of the Yuan dynasty. Our 018-016 ratio show quite high value, which suggests possibly draws. So we call this time period the late Yuan weak monsoon period. So indeed, there are multiple draws during that time, a lot of the peasant uprising. So one of the peasant uprising was led by Zhu Yanzhang. Later on, he led his soldiers and took the capital of the Yuan dynasty, which is where Beijing is now. So by the way, so his parents and his son all died during the drought. The Yuan itself also had a bad time with the climate. So if we look at our record again, through majority of the Yuan, our 018-016 ratio stayed pretty high. And particularly during the last few decades, the values of the 018-016 almost reached the highest over the last 2,000 years. So we call this time the late Ming weak monsoon period. So the last empire of the Ming Dynasty is the Chongzhen. He wasn't that bad. He was a pretty good empire by the time. However, he was lucky enough. As you can see, through most of his last administration, there are multiple years of the drought, starting from the 1637 to 1643. So in fact, the drought was so severe, it has been called in Chinese history, the never been seen over the 500 years. So that drought affected both the northern China and southern China, and of course, caused a lot of uprising. And the widespread drought also helped the rebel leader Li Zicheng to overthrow the Chongzhen in 1644. And Chongzhen Empire, he committed suicide in Beijing. So I hope through the last few slides and 5 time windows, I convince you that whereas other facts would certainly affect the Chinese culture, the chapters of the Chinese culture, the climate indeed have played a significant role. I mean, of course, the social problems, the political problems, the invasions, and the civil wars could also easily bring down the collapse of the kingdoms. But we want to argue the climate could play a significant role. So this is, in fact, is not something new. One of the ancient Chinese philosophers, at 2,800 years ago, he already said that very clearly. He said, dynasty would collapse if people were poor without harvest from water and land. In the past, the Xia dynasty collapsed when Yi and the Lo River dried up, and Shang dynasty collapsed again when the Yellow River dried up. I want to show you additional examples, I want to argue. So this is not just limited in China, in the ancient China. We could also see the similar examples everywhere else. For example, so one of the kingdoms once thrived in the Western Tibet, the Google Kingdom. So Google Kingdom started around 950 year AD. But around 1630, this kingdom disappeared very suddenly, very mysteriously. When this kingdom flourished, this kingdom played a significant role in terms of the transporting the culture, in terms of the economic roles to the Tibet, particularly for spreading the Buddhism to the heart of the Tibet. During the peak time, there are more than 100,000 population once lived in this region. It's a very harsh environment, but once 100,000 people living in this region. The interesting thing is, if we correlate to the starting of the Gurkhan kingdom and the end of this kingdom, they correlate just beautifully with the downtrend of the monsoon streams. It thrived during the time when monsoon was strong, but collapsed when the monsoon was very weak. Of course, since we have a lot of guests from the Europe, we probably heard already. So in the Europe, it's been also very well documented about alpine glacial retreat and advanced, and medieval warm period, the alpine glacial retreat, and during the Little Ice Age, the glacial advanced, mountain glacial advanced dramatically. The interesting thing is, if we correlate here, we can find the Song Dynasty almost match the medieval warm period, and the Ming and Qing can correlate to the Little Ice Age. Of course, the boundary between these two events could vary. The exact timing could vary from place to place. Lots of people already heard about the Viking colonized the Greenland. The coronation of the Viking started in 985 AD, the starting of the medieval warm period. However, the settlements in the Greenland was abandoned dramatically during the mid-14th century or as late as the 15th century, which is about the starting time of the Little Ice Age. So this is another very good, unfortunately also very sad example to show how a society was not able to adapt to the climate change. Of course, we can also see the similar example, the similar civilization collapse happened in Central America. So Maya was being very successful to flourish in the Central America. So they established lots of the monuments, just spectacular monuments in the rainforest. However, the classical Maya civilization collapsed around the mid-9th century. So our colleagues, they studied the marine sediments from the southern part of the Caribbean Sea. So what they look at is the trace metals. So this is they look at the titanium, which is very resistant to the chemical weathering, but it can easily be carried from the land to the ocean by the river water. So by looking at this time, around 850 to 900 years AD, so there are multiple years of the drought during that time. Of course, there are a few other hypotheses. For example, the tension between the society, the overpopulation, and the deforestation, the land use. But the climate change remains one of the very strong proposed mechanism to explain the collapse of the classical Maya civilization. So I hope I could convince you enough. So there are certain line of evidence we can look at. By looking at the paleoclimate records, we can study how that climate change could affect our civilization. But then, so what? What we can get? Can we use the past as a key for the future? Johan already showed some slides from the ISCO. The ISCO record, indeed, this is a part of the holy grail of the paleoclimate study. The truly international effort. So the group of the European scientists and the US scientists, They drilled the ice core from Antarctica, more than 3,000 meters long. What they're able to do that, they look at the oxygen and also hydrogen isotopic ratios from the ice. So they can talk about the temperature change, as shown here in red. Of course, the loss of the up and down here, which is corresponding to the interglacial time and the glacial time. Another dramatic thing they found is the change of the carbon dioxide. Because they were able to extract the carbon dioxide from the air bubbles being preserved in the ice. So this is a truly atmospheric carbon dioxide. Just for your point, just for information, so our modern human civilization was able to be flourished because the comfortable time zone for the last 10,000 years. We call it the Holocene. And another information I want to bring to your attention is, if you look at the carbon dioxide in the atmosphere change, for most of the last million years, 800,000 years, the carbon dioxide concentration in the air changed from around 180 parts per million in volume to 280 parts per million of the volume. However, if we look at today, for the last 150 years also, the carbon dioxide in the atmosphere, the concentration changed just dramatically, and today it's almost 400 ppmv. And consistent to it is the temperature. So the temperature increase after the Industrial Revolution is about 1 degree already. What we try to argue here is, by looking at the paleo record, we can characterize the pattern of the climate change and how the climate system can work. However, the human influence is clearly already exceeding the bounds of the natural variability. We are now already 7 billion of the population. We are already living the only blue planet in the solar system, and it's possibly the only habitable planet in the whole universe as far as we know so far. So if we look at Asia, we have the half of the world population here. So how to sustain the food security, how to maintain the water availability, all these issues, they're related. They're, to a large degree, they rely on the monsoon rainfall. So when I look at the paleo data we got, I look at what happened now. So I became less optimistic. But since yesterday's talk and today's talk, I think there probably is some hope. Although, of course, it's already challenging to forecast the Asian monsoon behavior because of the current, because of the future anthropogenic forcing. And on the other side, to predict the sociological, political, and economical consequence is even further challenging. But the previous speaker, Johan, gave a very, very good solution, or at least the direction of the solution. So now is the time for us to change our behavior. If we change our behavior, we can still save our planet. So at the end of my talk, I want to thank my colleagues in the US, China, and Brazil, and of course in Singapore, the US. I want to thank the funding agencies, NSF, NIF, and even private donation. Thank you.
provocative in that, huh? Question? Remark.
One of the reasons which dynasties were changed, absolutely correct, is because of the climate. But the reason was the concept of the son of heaven. When the emperor could not maintain good relations with heaven, it means a flood occur or any other disaster. Then there was an uprising, not just because of the floods, because son of heaven didn't perform.
Any other thoughts, comments, questions?
I have a question. Is rainforest has anything to do with monsoon?
Rainforest?
Yeah, has anything to do with monsoon.
Oh yeah, absolutely.
So do you mean that, generally speaking, if a country has abundant rainforest, then it is more likely for the country to be prosperous, right?
I mean, clearly the trees cannot survive without water.
I mean, for a country, if the country has more rainforest, then the country are more likely to be prosperous.
I think Johan showed that in his last talk that in fact rainfall was largely a function of how much vegetation was still around, right?
Yeah, that's a very good indication. So if you look at what happened today in Borneo Island and also in the Amazon, so if you maintain the rainforest, there's still some hope we can maintain the rainfall amount.
So do you mean that countries near Amazon, they are very rich countries?
In terms of the natural resources, yes. But of course, in terms of the GDP per capita, probably not.
Guaning?
Maybe two things. One a comment on the exchange just now, and the other one a question. I think what is really happening is China has been an agricultural country for a long time, and the prosperity depends on agriculture, which depends on the rain. I don't think that relates very much to rainforests and things like that. The question is, if you look at your chart, Ming and Qing dynasties are on the low side of the rain. They are relatively dry. Is there any interpretation you can put on that? Because for the whole of the Ming dynasty, it seems to be low.
So, of course, we here want to state it one more time. We don't want to say that climate change is the only factor that cause the survival of the dynasty or collapse of the dynasty. But when we look at the Chinese history, we did find some indications. For example, as you said, the Ming Qing in general, that was a time the climate wasn't favorable enough. In fact, that's also implicated. If the government, if the administration system worked well, can shift the resources from one place to the other, then they would be still able to maintain the dynasty. In fact, during the early Qing dynasty, the government used the Grand Canal very much because the northern part of China was in general dry because of the monsoon, right? So they used the Grand Canal to ship a lot of the food from the southern part of China, which where the rice could still be cultivated, to the north. So in a way, if the society can be able to adapt to the climate change, or the administration side can work well, so can share resources, so so there's still some hopes.
Peter Schwartz.
Two questions, one looking back, one looking ahead. You may have answered this question before I came in, so forgive me if you haven't, you just skip it. But one argument has been made that when China discovered how to grow rice in rice paddies and let the rice hulls decay in the water and produce methane approximately 3,500 years ago,
Right.
we saw a spike in atmospheric methane, and the argument has been it prevented another little ice age or major ice age. Do you buy that argument, number one? Number two, that's the backward-looking question. The forward-looking question is the current momentum of the system seems to be taking us toward at least a peak of somewhere around 550 parts per million, and the likelihood of stopping it much before then is very low. The last time we were there was about 65 million years ago when the whole world was tropical. Is that the likely outcome if we hit 550?
It's a very good question. So first one, you probably refer to what Bill Rodiman. So he was, he of course he proposed some anthropogenic, early on the anthropogenic forcing caused the greenhouse change. So basically he argued as human being, as the most intelligent species on the planet, we already changed the climate a long, long time ago, I mean back to the early of the Holocene. He probably right. He probably in terms of the methane, but not the CO2, because he basically came out of the two stories. One is to try to explain the CO2 change, and the other try to explain the methane change. He could be right in terms of the methane. Yeah.
At the 550? When we get to 550?
Or the second one, you know what? This is actually, we feel very struggled by looking at the paleoclimate data and what we observe today. If we look at the paleoclimate data, as I show you, as you also mentioned, the last time the carbon dioxide was as high as today is around 20 million years ago. 20 million years ago. That was a time, the very little ice sheet could exist in Arctica. There's no ice sheet at all in Greenland. So the sea level was way higher than today. Okay, so are we ready to head into that direction? So we feel very, very uncomfortable, very miserable when we look at the panel data and what we observe today. But in the other way, so why? So first, of course, the CO2 concentration. The second is the rate of the increase, the rate we put the carbon dioxide to the atmosphere. So this is incredible. As I show you the diagram, the ice core group that generated, that's on the time scale, the millennial or 10,000 years on such a longer time scale. But today we're looking at it's on decadal or 100 years. So if we look at the future, I'm not sure. And so this is a big uncertainty. But as the other side, I want to go back to what Johan said this morning. So if we do work closely between the different governments and everyone will change our behavior. So that still remains possible.
So Peter, if we really influenced the Holocene and made it the most stable... They want me to talk. Is it working now? If we really influenced the Holocene accidentally, maybe we could influence the Anthropocene intentionally.
One hopes.
One hopes. Question?
Yes. You see a drop in rainfall, drought conditions in China, but around that period of time, namely from around AD 700 to around AD 900, also very dry conditions, abnormally dry conditions in the Mayan region. In China, it was because, correct me if I'm wrong, due to the monsoon. The monsoons originated from originate from Indian Ocean, and Singapore benefited. This is the wind that brought talented people to Singapore from Yemen, from India, and then when the direction changed from China. Now, what is the mechanism in the Mayan region that also resulted in the same result of drought? Was it another kind of monsoon? What's the overriding force that in China it manifests itself, this force manifests as a monsoon carrying moisture, and depending on whether it's stronger or weaker, whether it covers a bigger or smaller area. Okay, how about in the Mayan region? So that's my first question. My second question is this. In one of your slides, you showed that there was a rebellion, basically a peasant uprising known as the Huang Chao uprising. Now, I noticed that they arose in the northeastern part of China. So I would like to have your comments on why is this so? If the pressure, because of the wind direction, is on China's northwest, so higher pressure, more suffering, more bitterness, no, people have nothing to lose. And why didn't the rebellion start in Chinese northwest rather than Chinese northeast in the form of the Huang Chao? Thank you.
Yeah, very good point. So the first one, we know the monsoon, simply the monsoon is caused by the temperature gradient, the temperature change between the land and the ocean. This is because the land and the ocean, they have a different heat capacity. So they have a different response to the heating. So most of the caves we're looking for are the inland of the China. So this is where close to the fringe. So in a way, the climate in that region are very sensitive to the monsoon, very sensitive to the climate change. So if we refer to the maritime, if we refer to where the Singapore now is, this, of course, the rainfall probably doesn't change very much. If you look at the history, probably the rainfall didn't change very much when the monsoon was weak or when the monsoon was strong, because in any way, it's always receiving rainfall from the nearby ocean. However, if we look at the whole, right, if you look at the whole, say if the further inland, there are peasant uprising, there famine happen, the peasant move around, they need food, so they need resources. So they could still cause some wars and the soldiers moving around. For your second question, if we look at the China, so the monsoon, sometimes we call it the summer monsoon, which is moving to bring the rains from southeast to the inland. We also talk about the northwestern monsoon, which is the winter monsoon. But clearly, it's only the summer monsoon brings rain. So Huangtuo uprising was able to start in the central part of the China, close to the east. That's where they used to be very rich in the food, very rich in the agriculture. That's also where it's very sensitive to the climate change.
Thank you, Xian Feng. That was an exciting talk that you gave. I'm from the Institute for Catastrophe Risk Management at NTU. Obviously, drought is not a good thing to most areas of the world, but monsoon is so too much water can be a problem with flooding issues, especially when you couple with high tides or other things. So I'm trying to see how, is there a possibility to look at the resolutions of this fluctuation of data which you show, if we're going to look forward in terms of risk management, because if fluctuation were in terms of tens of years or hundreds of years, it's pretty challenging for any society or government to do something significant for that long period of time. So what is the maximum resolution that technologies and methodologies that you are employing or forthcoming can bring down the resolution to how far you could see?
Yeah, this is very good. So in fact, over the last decade or so, we tried to refine the techniques, the technical part, to try to get the timing. For example, the timing better and better in terms of the boost accuracy and precision. At the same time, of course, we wanted to get a more robust record. So we're looking at samples from the different locations. So we want to study whether they could have geographically heterogeneity. I think there remains some hope with the development of the techniques. We can do better. For example, the record I show you for the last 2,000 years, the timing, the precision we can get is within a few years. So within a few years. So we can really look at the change of the pattern, of the monsoon pattern, on the resolution of the interannual resolution or decadal resolution. But again, we are facing another challenge is how to be quantitatively. So remember, we'll show the 018-016 ratio. So this is the isotopic ratio we could find from geological rock samples. But how that can be tied to, say, the rainfall amount is 1,000 millimeter, or 500 millimeter, or 1,500 millimeter. So quantitatively, there's still some challenging to do that.
TC, we can also use corals to get seasonal records of various climatic and salinity and so on. Another question here? Yes, sir.
Okay, yeah. Actually, I have one comment to just now the gentleman's question about why Huangchao's uprising started in the northeastern part of China rather than the northwestern part. I think one big reason here is like before the Huangchao uprising, there was already something wrong in the northeastern part. If you still remember, there was an 8-year war basically happening there. In the Chinese history, we call it Anshi Zhiluan, right? I guess we know that. So that area was like totally destroyed, and generated so many poor people, they simply cannot survive. And it's for them, it's just like either uprising or die. Well, either way, they have a good chance to die, so why not try? It's basically like that. I guess, yeah. In that, in that specific case, probably the war before the Huangchao uprising maybe was playing a bigger role. And then back to another case, which I feel like also I still have some doubt is about this Ming and Qing dynasty. Actually, we briefly discussed on that before. We know that according to the historical the data you have, the whole Qing dynasty was relatively rather dry. But however, we also know that the population actually boomed up during the Qing dynasty. One explanation was like, okay, we have this great canal which can actually deliver the food from the south to the north. However, that part of delivery was mainly to deliver to the capital city. It was not really for the regular people living in the west area, in the northern part of China. But even in that part of China, the population size actually increased quite a lot during the Qing dynasty. So one argument was like, that's mainly because one policy decided by the Kangxi, one of the early emperor of the Qing dynasty. That policy is like, if you have more boys, we will not really increase your tax. So people may feel like, well, it's better off to have more boys. It means like they are not really running out of the land. You have a more labor resources at home. You actually can, live better off. Meaning like they can still feed themselves. And if you have more people to grow crops or whatever, you can actually live better, averagely speaking. So then could we say, like during the Qing dynasty, in the quite big part of even the northern part of China, weather may not be a very serious constraint. Could we say that? I'm not so sure.
I do agree with what you pointed out. So the climate is one of the factors. It's only one of the factors, or one of the straw which bring down the camel. There certainly how the society worked, how the politics worked. When we look at the record, so we pick up these five time windows because they're clearly we can correlate to what we can find from the Chinese historical documents. By no means we want to say that you can just simply look at the Chinese history by looking at this simple curve. So clearly there are more. So this is a complex in any way.
This gets to the issue of resistance, right, or resilience that Johan was talking about in the previous talk, that the society is more resilient and it's more likely to survive some sort of a climate challenge or whatever. Other questions? If not, we're looking at an early coffee break. Do you have any idea whether it's ready for us, Jan?
I'm sure that it is. Otherwise, we just wait outside.
Okay, great. But we'll still come back at the same time for a Peter Ho's talk, right? Okay, so that is at 3:30. Okay. Thank you. Oh, I forgot. Fun to get
Thank you.